In this video, we're going to take a look at an exponential model, specifically the one for exponential growth and decay. There's actually a few different ones. This model is for exponential growth when there are no inhibiting factors. That means nothing to slow it down, so it's got tons of space and food and no predators, and it can just grow like crazy. So this is for exponential growth. It also works for exponential decay. That would be where something is either decreasing or maybe dying exponentially. So this is the model. A of t equals a naught e to the kt. Okay, that's the model for it. It could also be written as P of t equals P naught e to the kt, or N of t equals N naught e to the kt. These are all interchangeable. There's no right or wrong. A lot of times people will use A for amount, so like something in grams. P a lot of times is used for population, and N a lot of times is used for number of things. If you use A and somebody else uses N, it's really not a big deal. They're all the same thing. So looking at the A version, let's talk about that one. So A of t is a function. It's not A times t, it's A of t, P of t, N of t. So this is the amount at time t, and t will be specified by the problem. It has to agree with the rate, so it could be hours, days, weeks, years. It can be any quantity of time, but it's got to be consistent through the whole problem. A naught, that little sub-zero, is read as naught in math and science, and it always means the initial amount, and this is no exception. This is the initial amount. So A naught's initial amount, V naught is the initial velocity, and so on. E is the same E as we saw before. That's a constant, so 2.74, so on. That's a value. K is our rate. This is our growth rate or decay rate. If K is positive, it's growth, and if K is negative, it's decay. And you don't really have to memorize that, it just works out that way. It's something good to check, like if you know that your problem is that things are increasing, so you have more bacteria than you started with, then your K should be positive. So it's kind of a good thing to double check, but it'll work out that way. And then of course T is our time, and it needs to agree with our rate and our amount at time t as far as units. Okay, so A of t equals A naught e to the kt. Same thing for P. This would be population, initial population, same rate and time, and so on. All right, so let's look at an example. Most of these are set up like word problems. So let's say that we have 2,000 bacteria that are growing according to, and we're going to be given the equation for this one. So let's say we have P of t equals P naught e to the 0.2 t. Alright, so we're given the equation for this one. We're given the rate constant here, and we're going to use it for this problem. So 2,000 bacteria are growing according to this, and let's say we want to know, first of all, how many will we have in 3 hours. And I should have set up here where t is in hours. All the problems that I give you, hopefully they will agree. I won't intentionally give you one, but they might vary. So just make sure that the times agree. So how many will we have in 3 hours? So for sure this is time. Okay, you've either got time, initial population, or population after a certain time has passed. So 3 hours is definitely time. We're going to plug that in right here. The other thing that we need to put in is we need to put in P naught. P naught is our initial amount, and that's the amount that we're given right here. So we are starting with 2,000 bacteria, and we want to know what happens when T is equal to 3. So let's go ahead and plug those in. We're trying to find the population at 3 hours. So we're going to have 2,000 times e to the 0.2 times 3, and you want to make sure that all of that ends up in your exponent, whichever calculator you're using. Make sure all of that's up in your exponent. This is just a number, matter of plugging all of this in your calculator, and you might want to follow along at home. Make sure that you get 3644.237. Alright, now usually for living things we don't like to chop them up, generally speaking, so we don't want 0.2 of a bacterium. So we'll go ahead and round this to the nearest whole number. So it would be 3,644 bacteria. Just pay attention to what they're telling you in the homework as far as units and rounding and things like that. So a lot of times with living creatures, we go ahead and round them to the nearest whole number. So in 3 hours, we should have 3,644 bacteria. And that makes sense. We were starting with 2,000, and now we have 3,600. Okay, next question. When will there be 5,000? Okay, we know we're starting with 2,000. We know the growth rate. We want to figure out when will there be 5,000. So now this is the A of t. This is the amount that changes. So we're going to put this in for A of t. We've still got our same P naught, and this time we're trying to find time. So here, I'm going to rewrite the equation here so we can see where we're in P. Let me go back and fix that so it's not confusing. Again, they're interchangeable, it really doesn't matter. But let's be consistent. Okay, I'm going to write the equation just so we see where everything is going. So we know that our new population is 5,000, our initial population is 2,000, and we're trying to find time. So this is the equation that we've got. Now this time we're going to have to solve the equation. So this comes from the last section. We're going to have to solve this equation. So remember how we solve exponential equations? First of all, we want to get the exponential by itself. This is 2,000 times e. So I'm going to divide by 2,000. Now 5,000 over 2,000, you can reduce it, you can change it to a decimal, or you can leave it alone because it's going to go in the calculator, so there's really no point in messing with it. You just kind of open yourself up for errors that way. We can just go ahead and leave that alone. So we've got a number equal to e to the 0.2t. Alright, now how do we solve an equation with e? We want to do the opposite. The opposite of e is natural log. So we take a natural log on both sides. Or you can think of it as changing to a natural log. That would be okay too. ln and e cancel, which is what we want. On the left-hand side, I have ln of 5,000 over 2,000. Again, that's going to go in the calculator, so it doesn't matter if it's messy. And then our whole goal here is to get t by itself, so I'm going to divide by 0.2. Alright, now the way that I have it written here is how you're going to want to put it in the calculator. You need to make sure that you have these parentheses around the natural log so that the 0.2 doesn't end up in it or it doesn't end up out of it. And when you plug that into your calculator, you should get 4.6. That's rounded to one decimal place, so just make sure you pay attention to what the directions are asking for. So we get 4.6 equals t, and we are in hours. Let's make sure this makes sense. We started with 2,000. In 3 hours, we went to 3,600. And then in 4.6 hours, we went to 5,000. That all seems reasonable. Okay, the numbers are going to grow, and at times they're going to grow really rapidly, but they should either always be going up or always be going down. It can't go up and down, and the numbers can't look too crazy. Okay, so that's our first one. Now let's do another one, and you're going to see that it's very, very similar to this. It's pretty much the same steps every time. The numbers just change a little bit. Okay, next one. Let's say that we've got radioactive material. And it decays according to got A of t equals 100 e to the minus 0.3 t where the amount is in grams and t is in years. Okay, so radioactive material decays according to this equation. Now, if you haven't come across radioactive material in science before, I mean, you probably heard of it in the real world. The idea here is that you start with some amount of isotope, and what's happening is it's emitting little radioactive particles, and as it emits those radioactive particles, you actually have less of the radioactive material. The mass is still there, so if you start with, let's say, a gram, you're still going to have a gram when you're done, but less of it will be radioactive. So what we're looking at here is we're trying to determine how much radioactive material we have after a certain amount of time. And this is a big deal in the real world. A lot of applications in industry use things that are slightly radioactive, maybe not like uranium, but slightly radioactive. And it's really important to know how fast they decay, because that's important to know if they're dangerous, and then how long it's going to take them to decay, because you can't just throw them into a landfill. So these kind of applications are actually not terribly uncommon. They're real world. Okay, so back to our equation, A of t equals 100 e to the minus 0.3 t, and notice that our k is negative this time, and that's because we're decaying. We're going to have less of it as we go. Again, not something that you have to memorize, just something that's good to notice. All right, so part A. Okay, what is the initial sample amount? How much are we starting with? How much are we starting with? Well, you could plug in t equals 0, or you could just look right here. You're going to get the same thing. If you plug in t equals 0, anything to the 0 is 1. That becomes 1. And this is your initial amount. So remember our general form. Amount that changes is here. Initial amount is here, and that's not going to change. So our A naught is 100, and we are in grams. So we're starting with an initial sample size of 100 grams. All right, next one. How much will we have in 5 years? Okay, so this is a good question. How much of this is still going to be radioactive in 5 years? So that's going to be our time, and we want to plug that into here. So we're trying to find the amount when t is equal to 5. So you can do A of 5, or you can just say A equals 100 e to the negative 0.3 times 5. And again, you want to make sure all of that is up in your exponent when you put this in the calculator. All of that goes into the calculator, and you should get 22.3. And the amount is in grams, so we've got 22.3 grams. So if we start with 100 grams of radioactive material after 5 years, there's still 22.3 grams of radioactive material left. All right, part C. When will there be 2 grams? So let's say we want to know, well, how long are we going to have to wait until we're down to 2 grams of radioactive material? Okay, so this time we're being given an amount. We're being given an amount, and we're trying to find the time. So we're going to plug this in for our amount. So we're going to have 2 equals 2 equals 100 e to the minus 0.3 t. Okay, so 2 is going to go in for the amount, and now we need to solve for t. If you remember what we did before, there were 3 steps. Get e by itself, take a natural log, and then get t by itself. Same 3 steps every time. So first we're going to get e by itself. And then, let me come over here. You can see the steps. We still have them over here. Okay, so we get e by itself. We've got 2 over 100 equals e to the minus 0.3 t. And then we're going to take a natural log, because we want to do the opposite of e. That's the only way to get t out of the exponent. The opposite would be to take a natural log or change to natural log. Same thing. Ln and e cancel. So we have ln of 2 over 100 on the left side,